Okay, good day everyone and welcome to another video lecture. Today we're going to discuss the production functions. So what is a production function? It is described as the descriptive relation that links input with output. So you can have all these various inputs. So let's say we have this input 1, input 2, input 3. Okay? And then will all these inputs will go into a process. So this is the function which would result to an output. Okay. It specifies the maximum feasible output that can be produced for a given amount of inputs. So to put this mathematically, it is shown in this formula. X2 and so on. So we all have this various input that we're going to use in the production process. So let's have an example. Um, let's say you are making an auto part and it requires two inputs. Let's say steel and aluminum. Okay. So this will be used to produce an output, okay, which is the auto parts. So the S here is the pounds of steel and the pounds of aluminum. And let's say, okay, these two will what only comprise in the production. With this production function, we can have, let's say, 100 pounds of steel and 100 pounds of aluminum. So how many can we produce? Diba? So we'll compute this, we'll have 100. Okay? Let's say you have 400 pounds of steel and then you have then we'll have 100 pounds of aluminum. So we multiply this, we'll have 200, right? So this is an example of a Cobb-Douglas production function, which generally takes the form so this is an example of production function. So let's talk about the returns to scale. What is a returns to scale? It refers to the relation between the output and the proportional variation of all inputs taken together. And there are what we call the constant returns to scale, which is a 1% change in all inputs will result in a 1% change in output. So for our example, we have here our production function. If we change, let's say this one, okay? If we change 1% in all our inputs, so this becomes 101, and our aluminum also becomes 101. There is a 1% change. What would happen to our quantity of auto parts? Okay, so you compute this, you'll get 101. So this is the constant returns to scale. A 1% change in all inputs will result to a 1% change in our output. How about the increasing returns to scale? It is the 1% change in all inputs which will result in a greater than 1% change in output. The increasing returns to scale is usually illustrated through this production function. Okay? So, For our example, we have 100 pounds of steel, okay, and 100 pounds of aluminum. This will result to 10,000 quantities of other parts. What if there is a 1% change? What would happen? Okay, so for our steel, it becomes 101. For our aluminum, it becomes 101. There is a 1% change. What would happen to our output? Okay, so if we compute this, we'll get 10,201. Okay, so the change, okay, is more than 1%. This is the increasing returns to scale. Then we also have the decreasing returns to scale. It means that in a 1% change in all inputs, it will result in a less than 1% change in output. And it's usually presented through this production function. So for a 100 pounds of steel and 100 pounds of aluminum, what will happen to a decreasing returns of scale? It becomes 1,111.11. So there is a decrease in quantity. Data suggests that, through observation, larger firms suffer from decreasing returns to scale, way bigger, okay, than the smaller firms. Okay, through this is due to problems like coordination and control problems, which can become severe, well, for larger firms. Now let's discuss returns to a factor. What is returns to a factor? This refers to the relation between the output and the variation in a single input, holding other inputs fixed. So returns to a factor can be expressed as total, marginal, or average quantities. So what are these? The total product of an input is the schedule of output obtained as that input increases, holding other inputs fixed. While marginal product of an input is the change in total output associated with 1 unit change in the input, holding other inputs fixed. And the average product is the total product divided by the number of units of the input employed. So let's have this illustrated. So let's have the table. Okay? So this table shows the total, marginal, and average products of steel for the production function. So, as you can see, aluminum is fixed at 9 units. The total product of steel is the total output for each level of steel. The marginal product of steel is the incremental output from one additional unit of steel. And the average product of the steel is the output divided by the total units of steel. And if you look at the table, our total product for steel increases as our units of steel increase. But look at the marginal. The marginal product decreases. Look at the decreasing, no? The diminishing of the marginal product of the steel from 3, okay, the increase from 3 to 4.24. Now we have 1.24 for the marginal. Okay? From the total product, an increase from 4.24 to 5.20, our marginal product now is 0.96. From the total product, a shift from 5.20 to 6, our marginal product is now at 0.80. No? So as the total product increases, or marginal product decreasing, why is that? If you can recall the law of diminishing returns, no? Or the law of the diminishing marginal product, okay? So it states that the marginal product of a variable factor eventually will decline as its use is increased. So let's discuss the production isoquants. Most production function allows some substitution among inputs. Let's say you are the chief operating officer and you're managing a firm with a production function. We'll use our example. Okay, let's have the auto parts composed of steel and aluminum. And you are to target 100 units of auto parts. Now, there are various combinations that will form 100 units. You can have 100 pounds of steel and 100 pounds of aluminum. It can be that you have 25 pounds of steel and 400 pounds of aluminum. It can be that you can have 400 pounds of steel and 25 pounds of aluminum. All of this will be equal to 100 units. So an isoquant will allow you to show all input combination that produce the same quantity, assuming efficient production. So this curve is called the isoquant. Iso meaning the same and quant meaning quantity. An isoquant displays all possible ways to produce a given quantity. There is a different isoquant for each possible level of production. So we have this figure which shows the isoquants for a quantity of 100, 200, and 300 auto parts with the production function that we use. But the shape of our isoquant also vary. We have what we call the fixed proportion, the normal case, and the perfect substitute. In some cases, in which inputs must be used in fixed proportion and no substitution is possible. So the isoquant takes the shape of the right angles. And for extreme, no, there are perfect substitution where the inputs can be freely substituted for one another. We have our isoquant as a straight line. So these two are the extremes. So given that there are many ways to produce a given level of output, how do you decide which is the most efficient input mix? Diba? That is the question. There are many combinations, but what is the most efficient? So the answer depends on the cost, no? The cost of the inputs. Okay. Suppose that you face a competitive input market and can buy as much of each input as you want as its prevailing market prices. So the price of steel will be denoted as price of steel, diba? And the price of aluminum can be denoted as aluminum. Okay. So this would equal to the total cost, or the sum of quantities of each input used in the production process times in their respective prices. So an isocost lines display all combination of steel and aluminum with the same cost. Suppose that we have, let's say the price of our steel is at $50. Okay. And the price of our aluminum is at $1. Okay. And these are per pound. pound. So how do we illustrate this through a formula? Given that your total cost level should only be at $100. Okay? So, it is written this way. Plus, okay, dollar of aluminum. So, an isocost line display all combination of input that cost the same. So, for this example, at our steel, which is at $50 per pound, and our aluminum at $1 per pound, this figure shows the isocost line at $100 and $200 of expenditure. So within this line is a combination that will result to a $100 total cost and $200 total cost. Okay, isocost lines with the changes in input prices. What happens to our slope if there is a change in the input prices? 'Di ba? Our steel, its price is at $0.50 per pound. What happens to the slope if there is a price increase? Okay. So at $50 per pound, okay, this is the quantity of steel that you can buy. If there is a price increase, it will reduce. Okay, it will reduce because there is the total cost that you need to target. So at $1 per pound, this will what happen to your slope. So let's discuss the optimal input mix. So MP here is the marginal product of input. So in this production function, we have our steel, okay, the marginal product of steel and the marginal product of aluminum. So MP is the marginal product of input. So the ratio of the marginal product to price indicates how much additional output can be obtained by spending an extra dollar on the input. So this is the optimal input mix. So let's have this through a figure. So we have here our figure. Okay. With our low price of steel, okay, it's in this slope. Okay. With the high price of steel, it is in this slope. So here is our curve for our given output, the quantity of our given output. So this is what we call as the substitution effect. No? So the tangent here, okay, is the optimal input mix. So with the substitution, regardless, okay, you can use low steel or high price steel, okay, with the same quantity. The tangent here is your optimal input mix. With cost minimization, we have here our slope, okay, for um, 200 total cost, let's say, and this is the 100 total cost. And this is the quantity. So the tangent here, okay, is what you would be choosing, okay, the relevant isoquant.